Hello and welcome to Some Assembly Required, the CompuSAR project. We've spent the last two videos talking about timing diagrams. I'd like to show you how we use a timing diagram in order to determine which clock cycle needs to do which operations. Let's start with an overview of the CPU we've done so far. So these are the components in the CPU. This area contains all of the registers. The accumulator, X, Y, status register, program counter, and a latch for the ALU result. This is the data latch on the input. This is the stack pointer register. The ALU itself, which has no registers, it's completely asynchronous in operation. And the decoder, which in essence is the heart of the system. Now, I remind you that lines going in on the left of the module are input lines, and lines coming out of the right are output lines. What you need to understand about all output lines of the decoder is that, at least in my design, they are all latched and all latched on the falling edge of the clock. So on the falling edge of the clock, everything coming out here on the right gets fixed in place until the next falling edge of the clock. Going back to the registers, most registers use the rising edge of the clock to latch. So on the rising edge of the clock, the accumulator will take the data coming in from the data in, assuming write enabled is on, and latch it into the register and also output it, obviously. Same goes for X, Y, and the rest of them. The only register which isn't latched on this rising edge of the clock is the program counter. And as you can see, the clock line going into the register for the program counter has an inverter on the input. So the program counter latches on the falling edge of the clock. To understand why, we first need to remember 2 videos ago where we analyzed the timing diagram and the schematics for the 6502 and came to the conclusion that we cannot latch both the inputs and the outputs of our design. This is corroborated by the timing diagram of the 6502 itself, where we see that past the falling edge of the clock, we have a certain hold time, which for the specific voltage we've been analyzing, that's 3.3 volts, that's 10 nanoseconds. And then there's the address setup time, which is 40 nanoseconds. So we are allowed for 30 nanoseconds to have invalid data or invalid values on the address bus. And the purpose of this invalid values is to allow us to use asynchronous logic and give it time to settle before the correct address appears. Even so, you will notice that the address line follows the falling edge of the clock. So what we have here is that in case we need to output from the program counter, the falling edge is what triggers a change in the address, but the address needs to remain valid until 10 nanoseconds have passed. So entire area here, the address needs to be valid. And we're not allowed to latch the values between the program counter and the output. What all those in tandem tell us is that the program counter has to be updated on the falling edge of the clock. We cannot update it on the rising edge of the clock because then this timing diagram would not be possible. Now, it is debatable whether the 6502 updates anything on the rising edge of the clock, but I'm not bound to their design, so we are updating registers on the rising edge of the clock, despite the fact that that's a different design than the original 6502. In the future, I may revisit this decision, but not before all the opcodes are implemented. With that out of the way, let's do a sample opcode analysis. Let's pick a simple one. Load A immediate. Opcode A9. The datasheet says that immediate mode addressing needs to take 2 cycles. So Opcode A9 needs to take 2 cycles to complete and has 2 bytes, which makes sense. 1 byte for the opcode saying A9 and a second byte for the data to load into the accumulator. With that sorted out, let's start drawing the timing diagram. So first we draw the clock, as usual. Next, let's draw the address bus. We'll call this cycle 0 of the command, and we'll call this cycle 1 of the command. Ignoring the hold time and the invalid time for the moment, the address bus needs to update between the falling edge and the falling edge of the clock. So between here and here, the address will contain where the first opcode resides. Let's assume it's address 400. And of course, since we're reading the opcode LDA, the data needs to be A9. Now, you'll notice that the data is only valid for 15 nanoseconds before the falling edge of the clock and 10 nanoseconds after the falling edge of the clock. So it is only available a little before and a little after this falling edge of the clock where the 400 address was given. So our data line will say A9 and will be invalid the rest of the time. During the second cycle of the command, the address will read from the next byte over to read the immediate value to read. So this area will be 401. Let's assume the value we're loading into the accumulator will be D9. Now let's talk about the value of the accumulator. As we've seen before, the accumulator will only update on the rising edge of the clock. So only here will it become D9. Now, our whole reason for doing this timing diagram is in order to find out what control lines we need to output from the decoder and which cycle we need to output them on. So let's start with the accumulator load control line. This control line tells the accumulator to read its input from the data bus and load it into the register. Since the control lines update on the falling edge of the clock, we need this line to go high here. Since the control line is latched, that means that on cycle 1 of the load A command, we need to tell it to raise the load A control line, which will cause it to actually go high on the first cycle of the next command over and load the accumulator 1 cycle into cycle 0 of the next command. This is a bit confusing, but it's pretty consistent for all control lines. Since the control lines are latched, what we say on cycle 0 will only take effect during cycle 1. What we say on cycle 1 will only take effect on the first cycle of the next command over. So on cycle 1, we say load A, and it actually loads in the middle of the next cycle over. Actually, this isn't as confusing as it sounds because everything gets delayed. So on the decoder, we give a bunch of commands, they all get executed together, and while they are a cycle off, it doesn't seem so from the code. Here, let me show you. This is the handler for the LDA command. It doesn't include the actual memory access. This is done with a different part of the code. So the first time we're being called is during the last cycle of the address fetch, which for immediate value is just the program counter after being incremented. Which means that on the first cycle, there is nothing for us actually to do. If we look back at the timing diagram, that's because all we did is decode the fact that we're doing load A. There is no data for us to handle at this point. That's during cycle 0. All we can do is tell it, well, we need it from 401, to read from 401. Where the actual load happens is during the first cycle of the actual command, past the fetch cycle. There we instruct the following. We say that the data bus source is from memory. The control signals for reg accumulator write gets a 1. And we also need to update the status. If we look at the load A command, we see that it needs to update the negative and the 0 flags, which means that if the value we actually load into the accumulator is negative or has bit 7 set, then we need to set bit 7 of the status register, which is called N. Likewise, if all the bits in the value we load are 0, we also need to set bit 1, of the flag of the status register, which is called the 0 flag, which is precisely what we're doing here. We're saying that the status register needs to look at the data bus. We say that it needs to update the N register, which means copy it from its input. And we say that we need to update the 0 by calculating whether that's set. In other words, if all the bits it get here are 0, then the 0 flag will be set. Last, but by no means least, we call next instruction. This is a standard function that tells it that this instruction is done and we're ready to fetch the next instruction. Now here's the confusing part. While all of those are set inside cycle 1 of the load A instruction, they actually take effect during the next cycle because, remember, these values are latched. So they're set here, but they only take effect after this falling edge of the clock, which is why the A register gets updated here after we've effectively started running the next command. But as you can see, it isn't as confusing as you'd expect because all the control signals are set together and they interact properly. They are shifted by a single cycle, but they are all shifted by a single cycle. So not really a problem. But wait, we're also updating the program counter. And we're updating it multiple times. We're fetching the opcode from address 400, and then we're fetching the operand from address 401, and the next instruction over will be fetched from 402. On each cycle, we need to advance the program counter. Do we need to advance the program counter again for cycle 1 of the next command? You'd expect the answer to be, it depends what the opcode is. But if you think about it for a second, it actually doesn't. Address 402 will contain the opcode for the next command. But whatever it is, we're done. We've read it, we've parsed it, we don't need it anymore. So whatever is the next opcode, cycle 1 will be reading from 403. Well, it might be reading from somewhere independent, but the program counter needs to be 403. But wait, the program counter updates on the falling edge of the clock, which means that if we're to list the advanced PC control line, for it to advance from 400 to 401, it needs to be high during cycle 0 of this opcode. But for it to be high during cycle 0 of this opcode, it needs to be set high during the last cycle of the previous command, because this control line is latched on the falling edge of the clock, which means that we're setting it high here in order for it to latch here, in order for it to take effect here. So when we control the program counter, we actually need to be 2 cycles ahead rather than 1. So a beautiful, beautiful code here, all sitting together in harmony, affecting the control signals altogether, doesn't apply when the program counter is involved. When the program counter is involved, we need to actually think ahead. We need to be one cycle before the rest of them. With that in mind, let's look at the next instruction function. At the beginning of the function, we see an if statement that checks the interrupt state. This is our way of making sure there's no pending interrupt that waits to be handled. At the 6502 handles interrupts on the fetch cycle of the instruction. Having active interrupt equals interrupt break means there is no pending interrupt, so this is the standard handling for just another opcode. We set the timing counter to 0, that is literally this number here, the cycle number inside the same operation. Next, we say that in the control signal that we need to advance the PC. Again, remember this runs in the cycle before our opcode begins, which sets the advance PC for when cycle 0 arrives, which sets the program counter for cycle 1. Less confusing, we set the sync signal high. The sync signal is an external signal leaving the CPU itself that tells the outside device that we're now in the fetch cycle. It allows single stepping by cycling continuously until the next opcode arrives. Of course, in our case, the advanced PC needs to remain high because as we're fetching the first instruction, we already know that we'll be in the second one. However, since we already know we're in immediate mode, we already know that the next cycle is going to consume the data in 401. So we already know that the cycle after that will need to be in 402, which means that we leave the program counter high. Of course, in cycle 1, we call next instruction again, which again sets the advanced PC, which means that in cycle 0 of the next command, advanced PC will remain high. But let's assume this is a NOP, so that would be EA. Since the NOP already knows that it doesn't need the next byte over, it's going to lower the advanced PC, which will cause the next instruction over, which again will be instruction 0, cycle 0 of the instruction, to also be read from 403. And we actually see this in CPU execution. Here, let me show you. This website is called Visual 6502, and it simulates the MOS 6502 by actually simulating the individual transistors involved. Let's load the memory, A9, D9, and then of course EA, EA, which are the no operations. Click on the up button and the bus is updated. So, falling edge of the clock, the address bus says 0000, we're using a different address here. The data bus says A9, RW is 1, which means read, and for our benefit, it interprets it as load A immediate. Program counter is 00, and the A register is AA. This is the clock high part of the same cycle, and nothing changes. Cycle 1, address bus says 1, data bus says D9, which is what we wrote, and everything else is, and the program counter says 1. Everything else is pretty much as it was. So same goes for the high part. Cycle 2. We're already on to the next instruction. So the address bus says 2, the data bus says EA, but you'll notice that the A register is already updated. This is why I said that I know that this setup is different for the original 6502, because it updates the accumulator on the falling edge of the clock. You will also notice that the negative flag is high, because D9 has bit 7 set, and the 0 flag is low because D9 is not 0. So, first cycle of the NOP instruction, and we're from address bus 002, and the program counter is 002. Second cycle of the NOP instruction, and we see that the program counter increased to 3, because after all, we finished reading the opcode and don't need it anymore. And the address bus says 3, and of course, the data bus says EA because the next instruction over is also no operation. But the next instruction is again a fetch of a new opcode, but the program counter remains the same. And this is because we did not advance the program counter. We did not consume this value. We did not use it yet. So that's all I have for you today. I hope you've enjoyed. Thank you for watching.